we have learned the Pigeonhole principle in simple form. Today we will read the strong form of Pigeonhole principle, or sometimes we call this is the generalized Pigeonhole principle, and how it is applied to solve the different type of problems. So, first we see the Pigeonhole principle in strong form. We write that as a theorem. I give a theorem 2 because theorem 1 was the Pigeonhole principle in simple form. So, I write let Q1, Q2, Q3 and Qn are integers or n positive integers. If the total number of objects, say Q1 plus Q2 plus Q3 up to Qn minus n, since I have n number of n positive integers I have taken, plus 1, this many number of objects are distributed or are put into n boxes. Then the theorem tells, or the strong form of Pigeonhole principle, that then either the first box contains at least Q1 number of objects or the second box contains at least Q2 objects and so on. I can tell that the nth box contains at least Qn objects. So, I have these many positive integers. I have written Q1, Q2, Q3, Qn, then Q1 plus Q2 plus Q3 plus Qn minus n plus 1. These many number of objects, if I want to distribute among these n boxes, then either the first box contains at least Q1 objects or the second box contains at least the Q2 objects, and so on. In this way, I can tell that the nth box contains at least Qn objects. Now, how we can prove this thing? How to prove the Now, suppose we distribute the total objects, that is q1 plus q2 plus qn minus n plus 1, this total objects, this number of objects into n boxes. Among n boxes. If the distribution is such that for each I equal to 1, 2, 3 to n, the ith box contains fewer than or less than qi objects, fewer than qi objects. That means the distribution is such that each box, or say the ith box gets less than qi objects. That means q1, the first box, that is the first box gets fewer than or lesser than q1 objects. The second box gets lesser than q2 objects, and so on and so on. So, what will be the total number of objects if each box get lesser than the objects, that qith objects. So, I can write the total number of objects in, so the total number of objects in all the n boxes such that our distribution is like everyone, that every box gets fewer objects, is equal to say q1 minus 1, at least one less than q1. Similarly, q2 minus 1, q3 minus 1, plus qn minus 1, and this becomes q1 plus q2 plus qn minus n, since there are n boxes. So, this type of I have n terms. Now, if we add, so this is the total number of objects in the n boxes. So, now if we add one more object to be distributed, one more object to be distributed among these n boxes. So, my total number of objects become objects equal to q1 plus q2 plus qn minus n plus 1, that the last object that we have added, and the distribution we have done, or we have assumed that each box, see this, each box contains fewer than qi. That means, here ith box contains, here we have considered that qi minus 1. So, when we have added one object, so that object must have gone from the object, so the last object distributed that must be added any one among these, any one of the boxes among these n boxes. So, if it is ith box, if it is the ith box where the last item, last object is put, then the objects in the ith box becomes, earlier it was qi minus 1, now I have added 1. So, qi minus 1 plus 1, and that is equal to qi. So, the ith box contains at least qi objects, where I is 1 to n. So, it proves the statement in the strong form of Pigeonhole principle. Now, we see what are the other different way we can state the strong form of the Pigeonhole principle. Now, before that one, since we have told that many times the strong form of Pigeonhole principle is called the generalized form. So, we see that we can get the simple form from the generalized form or the strong form. How we can get the simple form? So, for simple form of pigeonhole principle, say if we put that Q1 equal to Q2 equal to Q3 equal to Qn equal to 2, then what are the total number of objects? So, total number of objects to be distributed among n boxes is 2 plus 2 plus 2 n terms. Since I have n boxes, then minus n plus 1. So, this becomes 2n plus n minus n plus 1 equal to n plus 1. So, that means n plus 1 objects, now this becomes n plus 1 objects distributed into n boxes. And each one will get 2 or more than 2, that means at least 2, since my Qi, Q1, Q2 is 2. So, in the strong form it tells that Qi, here Qi is 2. So, it gets at least each box contains at least 2, which is equal to that Q1, Q2, actually Qi. So, it is same as that of our simple form of pigeonhole principle. Okay. And what last day we have mentioned, last lecture, that when we have discussed the simple form, that we can take this thing as also a coloring problem. So, in terms of coloring problem, we can tell that if Q1 plus Q2 plus Qn plus n minus 1 number of objects are colored with n colors, and each one each object is colored with one color, then from the generalized principle we can tell that there is an eye such that there are at least qi objects of the ith color. So, any coloring problem we can, when we have to find out the number of colors or minimum number of colors to be is required, that we can apply our pigeonhole principle. Now, we see that this is our coloring problem. Now, we see what are the different other form we can write or we can state this generalized pigeonhole principle. You can write one that in our in the strong form or in the statement of the strong form of pigeonhole, if q1 equal to q2, q3 equal to qn equal to r. That means, I can write that if r plus up to n, that means inner minus n plus 1, these objects are put into n boxes then at least, since now all boxes have the same capacity and that is equal to R, then at least one of the boxes contains R or more of the objects. So, in one form we can write. Now, if I think from the elementary mathematics point of view, then also the strong form we can write a similar type of statement as that of our generalized pigeonhole principle. So, I can write that from elementary mathematics, that if the, now we take the average, okay, average of all q1 plus q2 plus qn objects. So, if the average of in the number of objects, I am taking some non-negative integers, in non-negative integers, and I am giving that integers are m1, m2 up to mn, and average is, if the average is greater than r minus 1. That means that is m 1 plus m 2 plus m n divided by n, this is my average, and this is greater than r minus 1. Then we can write that at least one of the integers is greater than or equal to r. Now, some other way, another form I can tell, I can write that if the average is less than r plus 1, that means m 1 plus m 2 plus m n divided by n is less than r plus 1. Then at least one is less than, then we can write then at least one of the integers, at least one of the integers is less than r plus 1. So, the statement of strong form or generalized pigeonhole principle, now we are writing for the elementary mathematics, for we are applying that thing for our elementary mathematics. And already for simple form we have seen that how numerical problems are solved using the pigeonhole principle, and that I think this is same as that of, I can write that if the average of n non-negative integers m1, m2, mn is equal to r, is at least equal to r, is at least equal to r, then at least one of the integers among m1, m2, mn satisfies that mi, any integer mi greater than equal to r. So, this is what we see, that simple elementary mathematics, that if the objects we write as the integers, and we can easily write that thing. Now, we see one application. We see one application of strong form. This is a very common problem. We write first the statement that a basket has 3 type of fruits. Or is being arranged out of 3 type of fruits, say apples, banana, and oranges. Now, problem is that what is the smallest number of pieces of fruit that should be kept, or that should be put in the basket, so that there are either at least 8 apples or at least 6 bananas or at least 9 oranges will be there. So, as it is, we can apply here Q1 is the strong form of Pigeonhole principle. Here Q1 is 8, Q2 is 6, Q3 is 9, and I have 3 different types of fruits. So, the total number of objects or total number of fruits should be that to be distributed is Q1 plus Q2 plus Q3 minus 3 plus 1. So, this becomes 8 plus 6 plus 9 minus 3 plus 1 equal to 23 minus 3 plus 21 fruits. So, we need 21 fruits. So, we need 21 pieces of fruits, and this is my answer. So, directly we can apply the strong form of Pigeonhole principle to solve this type of problem. So, with this we finish the concepts of pigeonhole principles, the simple form, the strong form, and some of the applications that how we can solve using this principle that we have discussed. And next lecture we will see again that how some different type of problems we can apply the pigeonhole principle.